Okay, in this video we're going to see an application of simple harmonic motion in the case of a swinging pendulum. So in this case, a pendulum is pulled back 20 degrees off center. So you can imagine a pendulum hanging due to gravity straight down. So this is center, but it's pulled back 20 degrees off center. So maybe something like this, where this angle is 20 degrees. And since it's pulled to the left to indicate direction, we will call it negative 20 degrees, okay? And the idea is, then the pendulum, this is at time 0, it's right here, it's released to swing and the clock starts ticking, and it takes a quarter of a second to reach the other side. So 0.25 seconds to reach the other side. Okay? What we can do, and of course at that moment, let's draw it maybe like this. When it reaches the other side, that would be positive 20 degrees. And of course, right in the middle here at center would be 0 degrees. So if we were to graph this motion, since we're wanting a function that represents the angle with respect to time, we would end up with a graph that looks like maybe something like this. This will be the vertical axis will be our time axis, and the vertical axis will be our angle axis, and that's measured in degrees. That's what we're interested in measuring. And then the horizontal axis will be our time axis measured in seconds. And so at time 0 seconds, the pendulum's position is at negative 20 degrees. So on the degrees axis we might mark negative 20 as our starting point for the pendulum. Okay? And then you can imagine as the pendulum approaches center, it's going to speed up. It's going to reach its maximum speed at the center. Okay? And of course that's going to happen halfway between 0 seconds and 0.25 seconds. That might be 0.125 seconds. Okay, so let's go ahead and do this. Let's mark some time measurements on our horizontal axis. Let's call this a fourth of a second. Then we've got a half of a second, and we can keep going as we need to by quarters, 3/4, 1 second, etc. So at 0 seconds, it's down here negative 20. It reaches its slowest speed, right? Or it's at its slowest speed, and then it's going to speed up, and at a quarter of a second it's going to be at a positive 20 degree angle. So at a quarter of a second it's going to be up here. So halfway between here, at an eighth of a second, it's going to be at 0. So it's going to reach its maximum speed there, and then it's going to start slowing down at a quarter of a second and come to a complete stop over here on the right side before it returns back to its original position. So another quarter of a second is going to go by, and like I said, it's going to end up back at negative 20 degrees, something like this. Okay, so that is, right there is one complete cycle. One cycle equals half of a second, right? And we could of course draw more cycles if we wanted to. Something like this. Okay? And so now what we want is a function that has this graph. Well, this is, remember the cosine function. Cosine usually starts up here at the maximum value, goes down to the minimum, and comes back up. So this function is a cosine function because it's not starting at 0. Remember, a sine function starts at not 0 necessarily, but the average value, like this. So the average value for sine is there, the average value for cosine is here. Okay? So this is the one we want, but it's flipped over. And remember, cosine typically is between -1 and 1. It's flipped over and stretched by 20, because instead of being 1 and -1, it's at 20 and -20. So this function, f let's call it, of time, t in this case, f of t, this is our t-axis, this is our y-axis, our f-axis if you want. F of t is going to be negative 20 times cosine. The negative is going to, because it's flipped over, it's multiplied by a negative, and stretched by 20 means it's multiplied by 20. So it's going to be negative 20 times the cosine of some expression, some argument here that represents whatever the angle input is to the cosine. Now, if you've watched my other videos on graphing trig functions that are much more straightforward, you know that the angle for one cycle of cosine is from 0 to 2 pi. So we need to figure out this angle now, right? That's what we need to do using x, because it may be confusing here calling it an angle, because I don't want you to confuse it with the angle that is measured on the y-axis, okay? I'm calling it an angle because it's an input to a cosine function, which we typically think of taking cosine of an angle. But let me give it a different name, which is also very common. It's an argument. I mentioned it before, okay? So we know that in a cosine function, the argument is between 0 and 2 pi for one cycle, okay? And in this particular graph, one cycle is represented over a period of half a second, right? One cycle is half a second. That's also called the period. Okay, so what does that mean? If we look at our t-axis here, one cycle for t ranges from 0, right, over here at 0 to 1/2. Okay? And so now, if I can change the 0 and the 1/2 to match my 2 pi and my 0 using algebra, then whatever expression is in the middle will be my argument that goes back in to my function. Okay? So what we have, there's lots of ways to do this. What I like to do is I need to focus on making this 1/2 into a 2 pi via multiplication. Okay? Make it into 2 pi. And the 0 I don't want to mess up because it's already the 0 that I want. So what I'm going to do is 1/2 might be difficult to work with. Maybe not for you. I'm going to show you a technique that is useful in lots of applications in mathematics. I'm going to take the inequality that we have here, and I'm going to change my 1/2 to a 1, make into a 1 first. 1 is very easy to work with. The way I'm going to do that is I'm going to multiply all three sides. Remember, whatever I do to any side, I have to do to all three sides. Multiply all three sides by 2, and so I still get 0 is less than or equal to, now it's 2t. You can see the argument here is changing 1. And so now I'm going to make my 1 into 2 pi. Okay? And so I can do that by multiplying all three sides by 2 pi. And so I end up with 0, which is good, is less than or equal to 2 pi times 2 is 4 pi t, is less than or equal to 2 pi. And so my argument, because I've got my 0 and my 2 pi, I know the argument of this trig function is 4 times pi times t. So the function, a function that represents this graph, this harmonic motion, is, so this is our function, f of t equals negative 20 times the cosine of 4 pi t, where t is in seconds, and f of t, the y value, is in degrees. Okay? So that's our function that we're looking for in this problem. if you want to check this, right, according to our graph, if we plug in 1/2, for t, our angle should be -20, right? So we can try that, we can check it out. Plug in 1/2 for t, and we want to see, do we get -20 for f of t, okay? So f of t equals -20 times the cosine of 4 times pi times t, which is 1/2 now, this is a times. So f of t equals -20 times the cosine of 4 pi times 1/2 is 2 pi, and f of t equals -20. The cosine of 2 pi is 1, and so for f of t we do in fact get -20. So you can see this function will tell us the position of the pendulum at any moment in time. The key here is taking what, sorry for scrolling so much, the key here is taking what you know about one cycle, right? One cycle, and that's going to tell you your range for your t values. So in this case it was from 0 to 1/2, and then you have to transform that into a statement that goes between 0 and 2 pi, which is what we got down here. And so once I've got 0 and 2 pi as my outer limits, I know that the middle expression represents the argument of the trig function.